Hello and welcome to my YouTube channel. In the previous video lecture, we have discussed about the Fourier series expansion of the function in the arbitrary period of length 2L, where the interval is particularly of the form 0 to 2L, L taking the any positive value. In this video lecture, we will see the problems where even though the interval is of length 2L, but it is of the form minus L to L. So how to deal with such examples, that we are going to discuss here. So let's start with the first example. Find Fourier series for f of x is equal to e power minus x in the interval minus 2 to 2. So here, as the interval is of the form minus L to L, so in case of integration, we have one standard property, that is integration from minus a to a of f of x dx is equal to 2 times integral 0 to a f of x if function is even, and it takes the value 0 if function is odd. So that result I am going to use here in order to minimize the computation. So as interval is of the form minus L to L, so that's why value of L is 2 here, and as this is the Fourier expansion for the arbitrary period, so therefore Fourier series is given by f of x is equal to a naught by 2 plus summation a n cos n pi x by L plus b n sin n pi x by L. And with this particular value of L as 2, it will reduces to the equation number 1. The function given is e raised to x. So let's evaluate the Fourier coefficients a0, an and bn. So a0 is given by 1 by L. See here, this is a problem of full range expansion, and as the interval is minus a to a and function is neither even nor odd, so that's why we need to evaluate all the coefficients a0, an and bn. So what is the value of a0? So in the formula of it will be 1 by L integral 0 to L f of x dx. Substituting the value of L as 2, so we will have such terms. On integrating this, we will get the expansion of this form. So therefore value of a0 is sin h2. Here we are using the formula sin h theta is equal to e power theta minus theta upon 2. So this simplification is optional. Even if you will write this much, then that will also work. Okay, so let's have the next Fourier coefficient, that is an is equal to 1 by L integral from minus L to L of f of x into, now as an is multiplied with cos n pi x by L, so in its formula you will always find cos of n pi x by L in multiplication with f of x. Okay, so this one should remember. Now substituting the value of L, now we find here the product of the form e power ax into cos bx. So for that we have a standard formula. Let's use that standard formula. So we need to identify the value of a and b. The value of a is here minus 1 and b is n pi by 2. Substituting this and using this formula, we will get this term. Now here we need to apply the limits. So see here, when I will put the limit, upper limit and lower limit in the second term, so it will become 2 will get cancelled. When I will put upper limit, so it will reduce to sin n pi, and the value of sin n pi, as it is known to us very well, that is nothing but 0. So for upper limit, this reduces to 0. Again we have lower limit as minus 2. So if I will put minus 2, so it will take the form sin of minus n pi. And what is sin of minus n pi? That is same as minus sin n pi. So that also gets reduced to 0. So this second term completely vanishes for both the limits, lower limit as well as upper limits. So let's see what is the contribution of this first term for the evaluation of the constant. So put the value of n as upper limit, that is 2. So what we get? E raised to power minus 2. Then here when I'll put 2 will get cancelled, cos of n pi. So we have minus cos n pi remaining constant term as it is. Now let's put the lower limit. So e power minus of minus 2, that is plus 2. So we have this one. Again cos of 2 will get cancelled, minus n pi is left, so cos of minus n pi. And as we know, cos of minus n pi is same as cos of n pi, right? So what we will have, so there are certain common terms. What are the common terms? So the common terms are nothing but here this 1 upon 1 plus pi square n square by 4, which I'll write taking the LCM, so it will be 4 plus pi square n square, and 4 will go in the numerator, so 2 will get cancelled with that. So what we are left with 2, 4 plus pi square n square, and then we have cos n pi, right? Cos n pi, that is nothing but minus 1 raised to n. So here it is missed. I have missed to write the value of cos n pi. It should be minus 1 raised to n. So please note this correction. Okay, then this is nothing but what? This is nothing but a if I will divide this by 2, so this becomes a sin h2, right? So we need to multiply and divide by 2, that's why here it comes 4. So value of an is nothing but 4 times minus 1 raised to n upon 4 plus pi square n square sin h2. Now let's simplify the next Fourier coefficient, that is bn. So it is again, the formula is 1 by L integral minus L to L f of x sin of n pi x by L. Here I have substituted the value of L as 2 directly. Now simplifying, putting f of x. Now we are getting the term of the form e power ax into sin bx. A is 1 and b is what? N pi by 2. So we have the formula for that. That is what? Integration of e power ax sin bx dx is equal to this one. Okay. Now using this and simplifying, applying the limits. So what we shall get? We shall get it as this step, right? So again, for the sine term, when I'll put upper limit, it will get reduced to sin n pi is 0, so first term 0. Again for lower limit also it gets reduced to 0. So we will have the expansion because of the what? The cosine term, right? So put the limit here, put 2 n as 2 to cancel cos n pi. Here also for lower limit, cos of minus n pi is cos n pi. So we have such type of terms. Collecting all the common terms and simplifying, you will find the simplification in this way, right? So therefore the value of bn is 2n pi minus 1 raised to power n. Minus 1 raised to power n is the value of cos n pi. Okay, simplifying, so we will have this type of terms. So therefore the Fourier series is nothing but obtained by substituting the value of a0. A0 is sin h2 by 2 plus an, this is an sin n pi x by L, plus bn, this complete term is bn, then cos n pi x by L. So in this way we can get the Fourier series expansion. So here we have seen the function which we have considered over here is defined over the interval minus L to L, but it is neither even nor odd. So here in that case we have to evaluate all the 3 Fourier coefficient. Let's see what will happen if we have the function over the interval minus L to L as either even or odd. So let's see what should be the requirement. So here we need to find out the Fourier series expansion of f of x equal to x in the interval minus 2 to 2, right? So we will first check this function for even and odd. So we just replace x by minus x. So what we find, this x is nothing but f of x. So what we are getting, f of minus x is equal to minus of f of x. So therefore f of x is odd. Again when I will compare this with the form minus L to L, so what we are getting, L is 2. So as function is odd, so for odd function there will be only a sine term. Okay, so therefore a0 is 0, an is 0 for all n, and hence the Fourier series is given by f of x is equal to summation over n equal to 1 to infinity of bn, as only sine term is required for an odd function, right? So sine of n pi x by L. This is the problem of the generalized interval or arbitrary interval. So here it should be in the angle n pi x by L. Put the value of L as 2, right? Where bn is given by 2 by L integral 0 to L f of x sine of n pi x by L, right? So on putting the value of L, we will have this type of terms. Now just as you can see here we are having a product of the algebraic term with a sign. So here in this case we will simplify this by using the the Bernoulli formula. So let's see what is the simplification. according to Bernoulli formula. So first function is x, integration of sine is minus cos n pi x by 2, then derivative of this is to be written on the denominator, so n pi by 2, then minus derivative of previous first term, that is 1, and again integration of this, so minus as it is, integration of cosine is sine n pi by 2x, and then n pi by 2, already n pi by 2 is there in the previous term, so it becomes square over the limit 0 to 2. So this one should note that when we have a case of even or odd function, so the limits of integration will not be minus L to L, it will reduce towards 0 to L, okay, and here you will find 2 by L, so this one should note, okay. So therefore applying the limit as 2, right, so obviously this second term reduces to 0 for both the limits, because here when I put x as 2, it will reduce to sine n pi, and sine n pi is 0, again sine 0 is 0. So I am having the value of this because of the this first term, so put x as 2 will get cancelled, cos n pi, right, and when I'll put x as 0, lower limit, so this term completely vanishes, so 0. So now using the formula cos n pi as minus 1 raised to power n, we will have the value of Bn as 4 by n pi, and by law of indices I can write minus 1 into minus 1 raised to power n as minus 1 raised to power n plus 1. So therefore we have obtained the value of Bn. Let's put it in the Fourier series which is given by equation 1. So we have f of x, which is nothing but x, is equal to, this is Bn cos of n pi x by L. L is 2. Now 4 being a constant, you can write it outside the summation as well. So this is the problem where I am having function as a odd. Let's have the problem where interval is minus L to L form and function is even. So that is f of x is equal to say x square. So when I will compare as interval is of the form minus L to L, so let's quickly check whether this function is even or odd. So replace x by minus x everywhere, you will find minus x whole square is same as x square, that is f of x. So f of x is even, right, as f of x is even, so we will have only constant term and a cosine term, that is given by a0 and an. So Bn will be 0 for all n. Okay, so Fourier series expansion is given by a0 by 2 plus summation an cos n pi x by L. L is here what? 1, so it is simply n pi x. Okay, where a0 is given by 2 by L. Remember, for even and odd, the formula will have a change, right? What is that? In place of 1 by L, it should be 2 by L, and limits will be 0 to L. So this one should remember, right? F of x dx. Substituting f of x, integrating, you will get a0 as what? 2 by 3. Now, similarly, an will be 2 by L, integration 0 to L, f of x cos n pi x by L. And then substituting L, simplifying, again we find product of two term, one is algebraic. So we will apply successive integration by parts. So applying successive integration by parts, the way I have told you many times in the previous video lecture, so many times we have discussed the successive integration by parts, applying that and applying the limits. So it will get reduced to this form. So remember, the value of cos n pi is minus 1 raised to n. So in this way we get an, and hence we can write the Fourier series by putting the value of a0 and an. Whichever are the constant term, you can write it outside the summation sign, right? So in this way we have seen when we have an arbitrary period of the form minus L to L, then very first thing that one has to do is to check whether function is even or odd. If you find function as even, then over there you just have to evaluate a0 and an, and if function is odd, then we need to just evaluate bn. But if we get the case where function is neither even nor odd, then it should be treated in the same manner as we did it for 0 to 2l form, right? Only thing is that the given limits must be written in the formula, that is a0 is written as 1 by l integral minus l to l form. Okay, so these, if you understand this, then you will find it easier to get the answer for such type of intervals. So far we have covered the problems of periodic expansion for the period of length 2 pi, where intervals are of the form 0 to 2 pi as well as minus pi to pi, and then we have considered the cases where interval is of length 2L, that is for arbitrary period, where interval is of the form 0 to 2L and minus L to L. And we have seen some deductions where the function is when the function is coming out to be the even and odd. So I hope these set of video you will find useful in order to get the Fourier series expansion for a given function. So I hope the concept must be clear to you all. In the next video lecture, we shall discuss the half range Fourier series expansion, right? When the interval is not of the length 2 pi, that is of the half of its length, that is pi, then how to solve such problems, that we are going to discuss in the next video lecture. Thank you all for watching the video.